Most likely YouTube manometer. There are many, of course. I'm just telling some typical example. YouTube manometer. Okay. Then we have two tanks in series. So our broader LLM is that first and second order systems are broadly available, like they are the most widely observed systems, processes that we would look into, but there are more complicated process, okay, more complicated dynamics. So in the first order system is fairly straightforward. It would have a numerator and denominator would be of this form. Numerator gain, denominator time constant times s plus 1. While second order would be slightly different. So it would have, of course, an additional term called zeta, which is the damping factor. So this is again a time constant. So this is the broader framework of first order and second order system. So see, what you would really see here is that there are no, so how this complicated dynamics arise. So that's something that we need to look into. First of all, there is no, in the plain vanilla case of this first and second order system, there is no numerator variable. So first of all, if there is a, this could be due to a numerator polynomial. Okay. This could be one of the reason, because then you would have some more term in the numerator. And second could be presence of irrational terms. So irrational in the sense that not polynomial. They are not reconcilable as polynomials. So what we will do in that case? So here we are of the very nice structure that things are polynomial and we are good to deal with it. Okay, so by the way, we have also learned two things in the middle. Okay, one is what is so numerator roots of transfer function. That is called zeros. Okay, and denominator roots. That is poles. Okay, so numerator and denominator roots and they have their own characteristics. So the poles would mostly responsible for stability. We'll talk about that. While zeros are mostly responsible for direction of the dynamic. So keeping this aside, so we have what we have seen last time is the consequence of 1, which is the numerator being a polynomial. So which essentially means that you have some zeros in the system. So presence of the zeros. So one typical and simple and typical example would be, let's consider a simple second order system, okay? Overdamped kind of, okay? So k into 1 plus, let's say, tau numerator s divided by 1 plus tau d1 is 1 plus tau d2s. So you're sure that there is a pole here, zero here, and there are two poles here. So what we have observed that if this Tn, which is the numerator time constant. Okay. If it is greater than 0, it's good. Okay, you have to look at the what you call the you have to look at the form. We are writing in exactly the same form as that of denominator 1 plus some towers. Okay, so in this particular form, okay, so if you're writing in something different like s plus, let's say a plus tau n s, and then that's different. So if you're writing exactly in this form, the presence of tau n greater than 0 lead to fast response, which is a good thing, unless if it become unstable. But when this tau n become less than 0, what you would really see that, okay, it would result in something known as inverse response, which essentially means that the slope of the system at t is equal to 0 is non-zero. So, which if you try to plot this, what would happen? Okay, at the starting point, let's say this is your y, of course, normalized conditions with respect to time. You would see any direction which is opposite to the overall direction. So your overall system might settle out here, but you see that there is a different direction maybe for a short time. So this region is basically the inverse response region. And so this is what we have learned. So first part of more complicated dynamics. Why it is more complicated? This is something that is not expected. So one example is we have seen is a distillation column. Increase of steam pressure in the reboiler. So what would happen is, so if you just increase the steam, there would be more frothing. So as a result, okay, so there won't be good enough boiling. So a lot of liquid would fall from the rise that just above the reboiler to the reboiler drum, which would result in increasing the level in the reboiler initially for some time. But of course, you are supplying more heat, so they all get vaporized after some time, and what you call the level would keep on decreasing. So this is just due to frothing. Lot of variables are getting increased, and as a result, it comes down. So so see, this is one example. So other example of inverse response, what we have seen is if you have parallel first order system. So which essentially means that okay, you have an input, okay, you have two systems, both of them are first orders. Finally, you merge them. You have only one input u, okay, you have a G1 and G2, it gets split upon G1 and G2 and again get merged, and finally you will get your Y. So what are we saying here is that Y would be, okay, or rather Y by U, I am deliberately omitting S, okay. So just omitting, I am deliberately omitting S as a U and S as a function, U and Y as a function of S. So Y by U essentially means that uh, G1 plus G2, assuming first order dynamics, let's say K1 by tau S plus 1, tau 1 S plus 1, okay, K2 by tau 2 S plus 1, which essentially means that when you all take the LCM and rearrange the variable, you would eventually get K1 plus, in fact, K1 times tau 2 S plus 1 plus K2 times tau1s plus 1. Okay. Then tau1s plus 1 times tau2s plus 1. You can further simplify this. Okay. Then it would be eventually K1 plus K2 because K1 is everywhere, K2 is everywhere. And it would be K1 tau2 plus K2 tau1, okay, divided by, of course, K1 plus K2. You can just keep it normal, it would cancel out times S, okay, plus 1. Okay, you have the denominator, which is tau1s plus 1 and tau2s plus 1. So what would happen here? So your original system did not have a 0. Once you combine them together, this brought in this particular term, which is which brings in a 0. Because there was no numerator term in these individual transfer functions. You see, there was no numerator term. Both of them having only denominator, but they connected parallelly somehow. This is quite happened. So this is a very common scenario in a system. So in a chemical process, let's say you have a flow coming in, you put it a splitter, and it goes to two. Let's say this is going to the reactor one, this is going to a reactor two. Okay, then eventually, so maybe for capacity expansion, you are not sending them into a single reactor for the time being. You do it with two parallel reactors, and their product that is coming out of this, you kind of blend it together for your final output. It's very common scenario that you would see in any industry. So your raw material is going to reactor 1, reactor 2, and finally this is your product. Very standard scenario. Each of them, let's say, assume with the first order dynamics as in here, but when they augment together, it brought in a 0. So this particular term now would control the dynamics of the overall system, which essentially means that if that variable, which is, I'm sorry, K1 tau2 plus K2 tau1 divided by K1 plus K2, right? Let me just look up. Yeah. If it is less than 0, you would see an inverse response, which was not originally expected. Because so this is also one thing that you would understand. So when you install things, the way they behave, it is different compared to when they operate standalone. So this is the networking effect of networks, effect of networks. It was not expected initially, but it brought in a lot of additional complications. So, any questions so far? This was one complicated dynamics that we would like, which was unexpected. So, any questions on this? Is this clear to all of you? Any questions? Okay, so if there are no more questions, I am moving further ahead. So we are now trying to see what is this non-polynomial terms that can happen in a transfer function, which was, and how they are going to affect your dynamics. So the key, what you call the key aspect of, or whatever the major source of irrational term in a transfer function is the time delay term, process with time delay. Am I audible to all of you? Any issue?
Yes, sir, you are audible.
Okay. So what is the time delay in a process? So this is a very common, like I would say most common. So you cannot imagine. So you might, so many a times you neglect the time delay. That is a very different aspect. But this is an ubiquitous thing. You cannot live with a time delay. Simplest example. Let's say you pedal your accelerator, for increasing the speed. So the time when you pedal, so you wanted to move from, let's say, your speed from 60 to 80. So the moment you apply your acceleration, there is some level of lag. Okay, so unless you are talking about a very sporty vehicle where you can increase the speed from 0 to 100 in 1 second or 2 seconds. In most of the normal vehicles, when you pedal, so when you push, like when you press your accelerator, and there is the engine would take some time to respond. So this is very natural because there are various interconnecting factors. The input that you have given. So what is your input here? So input that is given is your pressing your accelerator, which essentially means that more fuel will be burned. Okay, but that requires, let's say, nozzles to be open, more feed injector has to send in more fuel into the cylinders, burn it. Okay, so that takes a couple of seconds. Of course, it is not minutes, but again, some seconds. So what you really see here, so what I am trying to say, so let's say, so this is your input U, this is with respect to time, and this is your output Y. So let's say you put your, so and let's say this is the time, which I'll call it as T, when you are giving your, uh, when you are, when you are subjecting your input. So at that time there was no change, and you pedaled your accelerator whatsoever, and your input, and you retain that. So what would happen? So say let's say this is your T here. Okay, maybe I'll put T naught to avoid any. T is the general variable, T naught is the particular variable in this context. The response time that you would really see not at T, maybe at T1 at here. So you would really see that the speed is, there is no significant change in the speed, and the speed keep on increasing whatsoever. In what fashion it could be. So you would see that there is some lag. So this particular phase, which is the lag, generally represented by the way, represented by theta. So this is generally called as transport delay, many names. Time delay, okay. It's also called as dead time because there is nothing happens during that time. So and this is inherent in every system. See, we are talking about process control, but this is an inherent, this is inherent to system dynamic, very inherent property. For instance, you are taking medicines, okay. So the effect of the medicine won't come immediately, right? So there is a time window in which the medication has to be uh, inside your body and react, and the effects would start coming. So there is, this is delay is ubiquitous. You cannot live with it. So this is uh, uh, every now and then you would see in processes specifically. So these, the reasons for the time delay are flow. Okay, flow could be stuck at somewhere. There would be some, and if there are some solid materials in the conveyor belt, and many, so there could be many. So there's some blockage. Okay, some fouling. This is connection with the transport and also due to delay in sampling. So let's say, so you are what I would say, you wanted to measure the composition of a product of the distillate. So this is of course the feed, this is the reboiler, and this is the condenser, and finally the distillate. So here is the distillate. This is the reboiler reflux basically, and this is the feed. And you wanted to measure the composition of the distillate somewhere here. So you put an analyzer transmitter. So most of the time, so so in industry composition measurement, you can measure temperature, pressure. So there are two types of variables in overall process industry because few of them are very easy to measure. So one is temperature, flow, pressure, these characteristics. Mostly temperature, flow, pressure. Did I miss anything? Most of them. If you need conductivity, anything is okay. So these variables are generally easy to measure because the sensors are quite responsive. So the sensors that you would really need installed in a system to measure these variables are quite responsive. They are well calibrated, very fast, and so basically, of course, if there is a dead time, it would be only in seconds or even fraction of seconds. Well, variable like composition, this is a very, very, very difficult variable to measure. Why? Because this requires mostly analysis. So even if you take analyzer, transmitter, take the sample, it probably will have to go to a chromatograph. It could be gas chromatograph, it could be liquid chromatograph, or it could be an online high performance chromatograph. Because so generally composition measurements are done by means of performing a chromatographic operation. So these are very slow in nature. Fine. So which essentially means what? Okay. Let's say you wanted to measure something at T. Okay, you took the sample. Again, so let's avoid confusion. Let's assume that you have taken a sample at T naught and it has gone to the chromatograph and it takes T1 time to reach your real facility because in an industry, so these are very, very costly analytical instruments. So you won't keep them open ended inside a you don't keep it open in a what you call unattended environment. So there would be sampling labs were in which, so that's why there would be some piping, and that would reach to your lab. Okay, then the sample need to be fed into let's say at that time T2. You started feeding into the chromatograph maybe. So this is your chromatograph. Then you got the results at T3. So you see from T0 to T2, your sample kept idle. You don't know what has happened. So if you and it is not at the source also. You are taking sample from your sample is somewhere in your distillation column somewhere here, and your lab is, let's say, even physically located somewhere here. So you have to take it via piping. So meanwhile, you don't know what has happened. And your result comes out to be at T3, maybe after 10 minutes, 15 minutes. So it's a big problem. So every time this would induce a time delay. Any questions so far? Any questions, anyone? Is this clear to everyone? Any questions? Is this clear to everyone?
Sir, it's clear.
Okay. So how do you represent this mathematically? So time delay, which means that, so again, assume steady state condition. That's why it is 0 for t less than 0. You would assume that there was no change. So it is the physically your output is 0 between, so your input is right here. So you are given the input here and your output would be after some time. This is your y and this is your u, this is the time. So your output comes like this. So virtually there is nothing comes out, even though there is a change of input at t naught. I'll call this point as t naught. I'll call this point as t1. Between t naught to t1, nothing comes out. So y of t should be less than 0 for t less than theta. Okay. So let's say this is the starting time. Let's t naught is equal to 0. Then eventually what would happen? So your output would be u of t minus t. So your u is at here, but your output is theta behind that. So u of t minus theta for whatsoever for t greater than 0. So which essentially means that, so let's say at time is equal to 0, there is no output. If your time is greater than theta only, you would see some output, which is some value. You forget about that number. So what is that you would see here? So let's say this is your u, your output. Let's say you are getting exact same profile. There is nothing happens. Your y magnitude is equal to your u magnitude. What would happen is your u would be like a time translated output. So here at every time you can figure out it would be a translation theta. Every point here is a time translation. So again, our Laplace table says that if it is a time translated output, okay, the Laplace transform is e raised to minus theta is for a translation value of theta. So this is a very difficult issue here. So see, we are of the impression always that your transfer function, okay, would contain some numerator polynomial and denominator polynomial. So now you have got a term that is non-polynomial, exponential term, and you don't know how to deal with. So see, and all our analysis is of the impression that, see, our analysis are broadly based on the roots of numerator and denominator. So roots generally would have for a polynomial variable. So if you bring in an exponential term, your analysis becomes complex. And why it is more difficult, because we have moved into this particular domain to make things simpler. So now there is additional complexity, which we would typically would like to avoid. So what could be one workaround here? Can someone say? So what will you do with? So if you are working with in this particular system, and when you calculated the transfer function, you have seen, okay, unfortunately there is an exponential term comes in. What would you do? Anyone?
So we'll make approximation, I think, for
Cool. That is the simplest way to go ahead. You can approximate a non-polynomial term into a polynomial term whatsoever, because this is a complex thing. the simplest way to do is you approximate the complex term. So now the question is, how do you do it? So there, if you are an approximation, there are n options in the table. There are n options in the table. And you should be very, very careful. Why? Because which one would be which one? What I would say. What is the best approximation that you could think of? That's the overall thing. So simplest way again. So we know so this any non-rational expression could be rationalized by means of simplest option is use Taylor series expansion. We have used it for non-linear what you call non-linear dynamics. Convert into linear dynamics. Use the same. So e raised to minus theta s would be 1 minus theta s theta. So it is negative, so the alternate terms would be positive and negative. You see, if it is positive, it would be always positive. Since it is negative, exponent is negative, alternate terms would be positive and negative. So what would happen in this case? Okay, so you have both a first order term, you have got a second order term and a third order term. Forget about the fact that you can neglect the second and third order term as we have done in the first order Taylor series, then and we like prove error of the order of n square, which is fine. So let's say you limit your first order term here. Okay, so now what would happen? So your approximation would be okay by u of s by u of s times a1 minus theta s. So let's look back and see. If theta, so this particular term is negative means it is an inverse response, which is the whole thing. So now what is happening here? The whole thing is minus theta. So the exponent of s is minus theta. So which means that when you approximate, what you are inviting is something more. So one complicated problem is transferred into another complicated problem. So what are you inviting here? You are inviting an inverse response. Unnecessarily, right? So you had a time delay problem, so that you converted, so that you got it around by making some linear approximation. But that linear approximation, what? It's brought in a term that is 0, which is negative 0, technically speaking. So not negative 0, positive 0, which essentially means that you are bringing an inverse response into the system. So this was a big problem. So this approximation is okay, but I think you would really see. So what is expected here? So let's say you have your system is like this, and this is your dead time. This is y versus time. What have you done now? Okay, this was the original response. The approximated response would be now something like this. It might coincide. It would most likely coincide, but you would see you are bringing an unwanted inverse response over here. So then people have tried for better approximation. So for instance, Pade has brought in a very interesting approximation. What this approximation says, okay, your e raised to minus theta s, okay, could be approximated with this particular function. So can someone say why this which is equation 7, maybe better compared to equation 6? Can someone say that? Intuitively, can you think and say why this may be a slightly better option? Why this approximation come is a different question. But I think why this kind of an approximation is better than the Taylor series approximation. Can someone think?
Sir, I think
Intuitively.
Sir,
Yeah,
I
go ahead.
think the inverse response gets compensated because for the numerator the root will be 2 by theta, and for the denominator of that e raised to the power minus theta is it would be minus 2 by theta. So I think it get compensated.
Okay. So that precisely the answer. So see, you are bringing a 0 here. So here you are only bringing only one 0. Correct? While here you are bringing a pole and 0. So this pole and zeros will compensate each other to some extent. So the level of the inverse response that you would have here would be slightly lesser due to an additional. So anyway, you are bringing an additional 0 here. So to compensate that, this guy would have his pole in the denominator. So the overall what you call contribution would not be skewed towards the contribution from the 0. So the pole would also have some level of contribution. As a result, the level of the inverse response would be lesser. So what you would see here, so we will come back to that. Okay, so there is also a, let's say if you are not satisfied with the first order approximation, there is also a second order Paddy approximation. So which essentially means we would bring in second order terms in numerator and denominator. And what I'm trying to say is, if you see the exact response, let's say it is something like this, and G2 is second order Paddy and G1 is first order Paddy. You see that first order Paddy, so let me just now erase. You see that the first order Paddy has some inverse responses. While the second order, sorry. So if you just put, give me a minute. So there are two things. So one is Taylor series, second order, first order Paddy, and third is second order Paddy. So what you would really see here, if it is, of course, this Taylor series is not being shown, I suppose. So Taylor series would have a much bigger dig. Huh? The first order Paddy, the level of inverse response is much lesser. While G2, which is the second order Paddy, is kind of oscillatory. You see, it has some level of approximation like this. So this is what we wanted to say. That, and while the exact responses, of course, it doesn't have any problem. It just 0 up till here, then it takes off. So this is one way to kind of compensate by approximating the nonlinear with the irrational exponential term into polynomial. Again, so if you have an e raised to theta s, of course, this is the first order Taylor series approximation. And 1 by e raised to minus theta, you may assume that 1 by of this, and you can also write. So this is also a very different way of writing. You see, we have not seen it like this. See, e raised to minus theta naught s, okay? If you expand, what you will get y e raised to minus theta naught s plus terms with respect to corresponding to order of n square. So somebody has proposed if this negative brings in a problem, you can also do the assume the following. Okay, what is that? E raised to minus with theta not s. Okay, we write them as e raised to minus theta 1 by e raised to theta not s. So when you expand this, there won't be a negative. So because it would be theta not s. So this would be in this particular form. So what are we seeing here? So in this case, what you are adding a pole. Okay, in this case, you are adding a 0. And pad approximation is in between. You have a pole on the denominator and this, sorry, pole on the denominator and a 0 on the numerator. So pad comes exactly in the middle part. So any questions here? Any questions at the moment? Okay. So I will also talk about, we will talk. Okay, so we'll talk about this particular thing and maybe stop for today. So oftentimes, okay, let's say you have a complex function of this particular form. So this is what third order, okay, fine, and also 1 0. Very very complex. First of all, it has three. No, so eventually, if you would really like to see what you really need, so we need to get this is what third order. This is 0. So eventually we need to get g of t. How fast we can get? So we have moved to the space of Laplace or transfer function to make things simpler. But you would really see this has become very, very complicated. So it would be desirable, okay, if we have a very simple structure of this particular, which is like a first order plus time delay. This is a very standard or simplest model that you could think of. So what is this? This is a first order, of course, with a time delay. So such systems are generally called as FOPDT, first order plus time delay. So very handy compared to this complex 0 and things like that. Of course, but the problem that you would have is you would have a exponential, but much more simpler to handle. But if you need, you can again expand them and bring in to pole structure and things like that. So what Kochestar thought, okay. So the Kochestar point was this: if you can use time delay, if you can approximate time delay as polynomial, fine, which is what we have done here. We have converted all the time delay to polynomial. So his point was, why don't you do the reverse if the polynomial degree is large? Can we also transform the higher order polynomials as just time delay so that you will have a very simple structure with a time delay? Let's say this is a theta f by tau 1 plus 1. Very simple. First order. But you have a time delay, which is fine. So, but what you are significantly saving is in terms of the order of the overall structure of the model. So you can now simplify. So by using the principles of approximation of time delay as polynomial, can we also do reverse? Very fair question. And his argument that was, if you do that, your complex process would be simply represented as a system with a, of course, with a pole, okay, and a time delay, which is an artificially constructed time delay. Your original system might not have a time delay, but it's an artificially constructed time delay. So for which he has suggested, so there is some proof that shows kind of illustrate his arguments are all good. We kind of leave that. So what he suggested, okay. So here you see there are three time constants. So the largest one, second largest, and third largest. Of course, the largest one is the key. You cannot ignore this guy. It's like rate determining step in a. So I hope you have learned reaction engineering, right? So you talk about something known as rate limiting step or rate determining step, isn't it? Hello, am I
Yes, sir.
audible to you guys? So in that scenario, you cannot forget about the largest time constant. So you retain this, okay? So if there are others, so the smallest time constant might not be of that important. So, but maybe second largest, maybe the largest, of course, you'll have to retain. And there are second largest, third largest, and things like that. Some of them you may be able to ignore, some of them you may not. So he was of the opinion as follows. So if there are the largest neglected time constant, okay, you half value of that is being added to the time delay if there is any, and the other half is added to the smallest retained time constant. The time constants that are smaller than the largest neglected time constant are approximated as time delays using this particular term, because now the polynomials can be approximated as a time delay. So if there is theta, you should be able to write them as e raised to minus theta as. So what he suggested in this particular case, okay, you see, so this is a third order system with three poles and one stable. What he suggested was very interesting. You see, the smallest. So let's take this. So let's take the 0, which is 0.5s plus 1. 0.1s plus 1 would be now e raised to 0.1s. This is something that we have learned, because the way it expands, how it would expand 1 minus 0.1s plus higher order. So you do the reverse and converted it into an exponential term. So now there are three more terms. 0.3s, 3s, and what you call 0.5s. So here, what would happen? So 1 by 3s plus 1 would be, okay. If you use the same principle, it will be 1 by, not 1 by, this would be 3s. So this 1 by s plus 1 would be raised to minus 3s. The same applies here. So what did you do? You retain this guy. The largest time constant is retained. Rest all are now converted as time delay. So there was not originally there was no time delay in the system. Now it would be 3.5 plus 0.1, 3.6. So the complex, or rather the modified transfer function uh, is this, okay, k e times, let's write this over adjacent to this. Okay. So this is now approximated as k times e raised to minus, I think, 3.6 s by 5s. So this is a very, very simpler structure compared to this complex. So the thumb rule here is we will stop at this moment and we'll continue on other such techniques. Okay. So if there are so what we are learning is regarding more complicated process. This more complicated is essentially a problem. So we will have to look for various levels of approximation to make it simpler. So what we have learned is, okay, so time delay is a contributor to the approximation. So you can do that and convert them into polynomial. Somebody also taught the reverse. If your polynomial could also be converted as a time delay if you can manage time delay. So this arguments went back and forth, and you could able to kind of simplify your system in various ways you want. So we will stop at this moment and we will continue from here in the next class. Any questions if you have, we can discuss it right now. Any questions at the moment? Any questions? Any questions? Is this all clear to you, all of you?
Yes, sir.
Okay. So if there are